Okay, welcome. In today's class, we are going to talk about gear design. In last class, we talked about the basic concepts in gear design. In today's class, we will talk about the gear design process. What are all the equations involved in gear design? We will also look at the nomenclature. So what are the parts of a gear? And then we will look at what are the strength calculations, what are the wear calculations that we need to do to design a gear. In last class, we talked about different types of gears. In today's class, we are going to talk about specifically design of spur gears. Design of spur gears. And I'm going to spend a lot of time on design of spur gears, because once you understand the design of spur gears, all other designs are exactly the same. For an example, when we try to design a helical gear, wherein the gear teeth are not parallel to the shaft, but they are at an angle, helix angle, what we do is we convert that helical gear into an equivalent spur gear and design the gear. So the idea is, once we understand the fundamental concepts of spur gear, same principles can be applied for all the gear designs. Now, can someone quickly tell me, and this is a very important question that you may get asked, what is law of gearing? In other words, what do you want to make sure if you want a smooth transmission? The other way this question can be asked is, if you hear a transmission box is making a lot of noise, what is kinematically wrong with that transmission? So all these questions, they are the same, like what is law of gearing? Correct. And remember this, because this is a fundamental kinematic relationship for gear transmission. If you hear a noisy gear, a technician may say, hey, the gear tooth broke or gear went out of alignment. But you know, kinematically, that means that the point of contact is not on line of centers. If you get a chance to design the cams, if I get a chance to teach you cam design, this point of contact on line of centers is a very important concept that allows us to simplify super complex mechanism into something called as equivalent mechanisms, which means from kinematics point of view that a very simple mechanism represents this super complex mechanism. And we will talk about it if you get a chance to study cam design. But let's focus on the spur gear. So if I were to draw the spur gear would look something like this. So spur gear would have something called as the pitch circle diameter. And what are the two types of profiles that are used in spur gears, or any gear for that matter? Gear tooth profiles. What are two types of gear tooth profiles that are used in gears? One is involute profile and the other one is cycloidal profile. So let me show you the sketch. And most of the times you will see the involute profiles, but sometimes you will see the cycloidal gear profiles as well. So this is sort of the three-dimensional representation of the gear. So what do we have? Imagine gear originated from friction wheels. So what you see here is you see an imaginary circle that is sort of at the center of the gear. That is a friction wheel representation of gear. What does that mean? It means that imagine if you have a mating gear, then these two gears would mate or assemble at this friction wheel diameter, which is called as the pitch circle diameter. Now, this distance, what you see on top, it's called as the face width. This is called as the top land. Now, the top part of the gear is called as the face. Bottom part of the gear tooth is called as the flank. And the most important dimension in the gear is something called as the circular pitch. So this distance, it's called as the circular pitch, also called as CP. So circular pitch. Now I'm going to show you the radius of the gear. So this is the radius of the gear. If you extend it, you're going to have a diameter of the gear. The important relationship for the gear is D is equal to the pitch circle diameter is equal to module M times T, which is number of teeth. Remember this equation. This is the design equation for the gear. So diameter, pitch circle diameter is equal to module. M is module. And T is number of teeth. Now for a gear pair, so if you have a pinion and you have a gear, the module has to be the same. Otherwise, those two gears cannot assemble. So M, the module, is one of the most important parameters for the gear. Now let's look at this thought exercise. Circular pitch is the distance on the pitch circle diameter between the successive teeth. Once again, circular pitch is the distance on the pitch circle diameter between two successive teeth. If the diameter of the gear is D, the number of teeth is equal to T, what would be the circular pitch? So the question is, if the diameter of the gear is D, if number of teeth is equal to T, what is the circular pitch? If you think about it, circular pitch is nothing but the perimeter of the pitch circle diameter, that is pi times D, divided by number of teeth. So circular pitch, CP, is equal to pi times the diameter, which is the pitch circle diameter, divided by T, which is number of teeth. Now please understand, from the previous equation, I can say D divided by T is equal to M. The first equation on the top, D divided by T is equal to M. So I can replace this guy by M, and circular pitch is pi times M. Everyone understood this? Now, what is gear design? And I'm going to tell you one simple statement. Gear design, and remember this, gear design is nothing but determination of module. Nation of module. Because all the parameters like the face, flank, clearance, all that stuff is defined in terms of module. Now, what other important parameters are for gear are important? So this top part, if you look at the tooth, and I believe I kind of alluded on this. So this part is called as addendum. This part is called as dedendum. Now, if you have a circle that of diameter that passes through the top of the tooth, which is called as the addendum circle. Addendum circle. If you have a diameter of the circle that passes through the bottom, this is called as the dedendum circle. Now, I want you to understand the addendum of the mating tooth mates with the dedendum of the other tooth. So what that means is dedendum has to be slightly greater than addendum so that the tooth can enter and exit. So there is some clearance. So dedendum is equal to addendum plus clearance. So which means that the distance, this is very important, this is the pitch circle diameter. This distance is greater than the distance from the top. So this distance is addendum and this distance is dedendum. So top is addendum, bottom is dedendum. Now, once again, I'm going to write this down. PCD. PCD stands for pitch circle diameter, is the diameter of a friction wheel. If gear is replaced by friction wheel. Now, another important thing that I want you to remember, the module must be same. Must be same. You cannot have a 5 millimeter pinion, 5 millimeter module pinion meshing with 10 millimeter module gear. Now, it is impossible. And once you decide to design the gear, all said and done, gear design means determination of module. And we will talk about how to determine the module using the beam strength and other equations. So if you look at the gear, here are some standard dimensions of the gear. So first and foremost, these are, first let me write this down, gear dimensions are proportional to module. So what does that mean? It means addendum is equal to 1 times module. Dedendum is equal to 1.25 times module. Working depth is equal to 2 times module. Minimum depth is equal to 2.25 module. Tooth thickness is equal to 1.5 times module. I did not show you tooth thickness. This is tooth thickness. So this is tooth thickness. This is tooth thickness. Clearance is equal to 0.25 times module and the fillet radius. So typically here there is a radius. So this is the fillet radius. Radius is equal to 0.4 times module. Everyone understood this? Now, at this point, let me explain to you. When we look at the gear design, we are going to use a lot of data. So we need access to a data book. So the good news is all the information that we need about the strength of the material, the proportions of the gear, standard nomenclature, standard practices, factor of safety, velocity factors, all that stuff is given in the textbook. So I would strongly recommend that if you have the hard copy of the textbook or the soft copy of the textbook, please open that and let me kind of walk you through the important tables, the design tables that we are going to use as we study the gear design. Because when we look at the gear design, depending upon the material, depending upon the type of gear, depending upon the operation, depending upon the working conditions, the factors change. So what I want to do is, let me just walk you through uh, the important tables. So I'm looking at chapter 28, which is Spur Gear design. If you have the textbook, please open it. If you have the textbook in the soft copy format, please open the textbook, chapter 28. So in chapter 28, we just looked at the external, internal gearing, the different terms used in gears, condition for constant velocity ratio, which is law of gearing. And then what I want to talk about is, please look at table 28.1. So table 28.1 gives you the standard proportions of the gear system that I just wrote. There are 3 different subsystems. You can have a 14.5 gear, you can have a 20 degrees gear, a pressure angle, or you can have 20 degrees stub. So 28.1 gives you the standard proportions of gear system. Now the next important table, and this is what I want you to remember, and I will write this down in case if you don't have the so table 28.2, 28.2, which is on page 1034. Now this table is an important table because please try to understand, we don't want gears to interfere. So let me ask you a very simple question. Imagine if you have if you are cutting a spur gear, have you seen anyone seen spur any gear? Let me call you with 3 teeth, gear with 3 teeth. Have you seen any gear with 3 teeth? Have you seen gear with 5 teeth? No. You don't cut gear with 5 teeth. Why? Because you need minimum number of teeth to avoid interference. And that comes from the geometry of the gear. So basically, if you have a 14.5 degree gear, pressure angle gear, you need minimum number of teeth. Otherwise, those two gears will bind into each other. They will eat each other. So there is minimum number of teeth that are required for gear to function, to engage and disengage. So table 28.2 on page 1034 talks about minimum number of teeth on pinion to avoid interference. There are two ways, and again, just like any design process, there are two ways to find minimum number of teeth. There is this big complicated equation which is below, and I will write this equation down. So there is this equation. To be honest with you, I don't remember this equation, so I need to refer to the data book to write this equation down. So this equation you can use to find minimum number of teeth, and this comes from the geometry of the gear. 1 plus 1 divided by G, 1 divided by G plus 2 sine square phi, where phi is the pressure angle. And please note, square root is up to this, minus 1. So what you do is, you basically, there is something called as AW, which is a fraction that you select. There is gear ratio G, there is pressure angle, and you substitute all these values and it gives you the minimum number of teeth. But what I usually do is, I follow a very simple guideline, which is given in page table 28.2. So in 28.2, if I'm designing 14.5, which is the pressure angle. What is pressure angle? Can someone tell me? Pressure angle is a line of action of force. The angle made by the line of action of force with the perpendicular to the interface. So if you have two gears that are meeting, for friction wheels, the force would be in the straight line, but since the gears are cut, you will have a certain angle, and this angle is called as the pressure angle. So this is the pressure angle phi. Now, if the pressure angle is 14.5 and the gear is full depth involute, so involute, then minimum number of teeth are 32. If you have 20 degrees pressure angle, you have full depth involute, you have 18. And if you have composite 14.5, or if you have stub involute, then the gears number of teeth are 12 or 14. So the idea is, you select what is the pressure angle that you want, or sometimes they will dictate, or they will say that this is the pressure angle that we want. Then you select the type of tooth that you want to cut, or type of gear you want. You want involute, you want stub, you want composite, and then go to table 28.2 and find the minimum number of teeth. Everyone understood this? Now there is a trick that you can do. I usually, if nothing is specified, I just say minimum number of teeth is equal to 18. So that just from my design experience, I just say, okay, I'm going to use number of teeth is equal to 18. Now, another important table that at this point I want you to take a look at, and this is super important, is look at table 28.3. So next is table 28.3. 28.3. This table 28.3 gives you the material properties and this is on page 1035. So please, online students, if you have access to the textbook, please open the textbook, hard copy or soft copy. And it is very important that you're familiar with all these tables, because this is design data. You cannot remember it. Whenever you are going to design, you have to go to the design data book and grab the information that you need to design that particular component. Material, then you have condition, then something called as BHN, Brinell hardness number, and tensile stress, tensile strength. Now, before I talk about different aspects of this table, can someone tell me what is BHN, or the Brinell hardness number? Right. So hardness is the property to resist scratches. Brinell hardness number tells you how hard the material is. For an example, if you talk about diamond, diamond would have very high BHN. Now, this table is important because it gives you the different materials, but please understand, different materials, that they have different properties. Not only that, different materials with different heat treatment have totally different properties. So I want you to carefully look at the table, and please see, for cast iron, depending upon whether it's cast or whether it is heat treated, the Brinell hardness number and the tensile strength values are different. Are you with me so far? Please look at cast iron grade 35. Cast iron grade 35 as cast and as heat treated, they have different BHNs and different tensile strengths. Everyone understood this? Moving on to carbon steel. Depending upon the percentage of carbon, the properties change, and whether it's normalized, whether it is hardened, tempered, the properties of hardness, properties such as hardness and properties such as tensile strength would be different. So you want to be very careful about the type of material that you are selecting, or the type of material that is specified, type of heat treatment that is specified, to select appropriate hardness and appropriate tensile strength. Everyone understood this? It's very important that you make yourself familiar with this table, and this table continues in the back. So please understand the material, please understand the condition, and that is super duper important. Now, let's talk about, if you were to design the gear, what is the fundamental failure mode of gear? So let me draw a very simple sketch for the gear. Okay. So you have this gear, something like this. Gear is transmitting torque. So torque means you have a tangential force, WT. You have the pressure angle. So basically, you have the pressure angle, and this is the pressure angle phi. So all said and done, can I represent this gear, this simple gear, approximated like a beam? So what I'm going to say is, at the first level of approximation, I'm going to assume that what I have is, I have a beam. And on this beam, there is this load WT. This is my first level of approximation. This is the height, which is h. This is the thickness. And if you look at, if I were to draw the three-dimensional view, this is going to be the width. So what I'm going to do is, I'm going to use the equation for bending. Sigma is equal to m divided by I multiplied by y. You agree with me? I'm just looking at the gear tooth at just a simple beam of rectangular cross section that is loaded by WT, and that is going to bend at the base. So M is nothing but WT, since WT is acting here, so WT multiplied by H divided by BT cube by 12. Multiplied by T by 2. So I have this beam strength equation. Now what I'm going to do is, I'm going to make some simplifications and then find out. I'm going to take WT on one side. So WT is equal to, I'm going to call this sigma B. Sigma B multiplied by B multiplied by T square, because check this out, there is T cube in the denominator, T in the numerator. So I have T square divided by 6H. Now here is something interesting. This T dimension and this H dimension, they depend upon M. So this T dimension and this H dimension, they depend upon M. So what I do is, I rewrite this equation as sigma B multiplied by B multiplied by a factor. And how does this factor come into picture? So let me give you the equation for T. T is equal to a constant of proportionality X multiplied by pi times module. Remember, pi times module is nothing but circular pitch. And T, which is the thickness, is proportional to pi times module. H, which is the height, which is proportional to K, pi times module. Again, X is a constant, K is a constant, but at the end, they are proportional to pi times M. In other words, T is proportional to module, K is proportional to module. So this equation, all said and done, takes the form of x square PC square divided by 6 K PC. And then finally, this equation WT is going to become sigma B multiplied by B multiplied by PC multiplied by x square divided by 6K. So this is the equation. However, I haven't told you what is the value of X and what is the value of K. But at this point, what I want you to do is, I want you to remember this equation, something like this. WT, what is WT? WT is the force. Do you agree with me? So this is, so I'm going to write this down for my own satisfaction. This is force. What is sigma B? Sigma B is stress. stress is given as Newton per millimeter square. Do you agree with me? So B is the face width, which is given in millimeter. PC is the circular pitch, which is pi times m, which is again given in millimeter. X is a constant of proportionality. K is a constant of proportionality. So do you agree with me that this big term that you see here is nothing but a constant? And the left hand side of the equation is force in Newton, and the right hand side of the equation is Newton per millimeter square multiplied by millimeter multiplied by millimeter. So can you see the left hand side is equal to right hand side? The only difference is we have x square divided by 6k that is floating around. Okay, and that x square by 6k is replaced by a factor which is called as y, and that is called as Lewis factor. So I will repeat, let me repeat this once again. What I have derived is called as the beam strength equation for gear. Why is it called as the beam strength? Because this comes from the bending equation. So in the bending equation, we have the bending moment. Bending moment is Wt multiplied by h. Wt multiplied by h divided by moment of inertia multiplied by the distance from the neutral axis. So, but for gears, the value of h and value of t is proportional to circular pitch. Then we substituted those constant, and finally we got an equation which boils down to something like this. It's super simple to remember. On the left hand side, we have Wt. On the right hand side, what we have is sigma multiplied by, I have B multiplied by, I have Cp, circular pitch. What is the equation for circular pitch? Pi times m multiplied by a factor y. And this is called as Lewis form factor. And depending upon the type of tooth, depending upon the pressure angle, this value of y is given to us. So now let me give you some historical perspective on this form factor. So if you look at the gear designs, engineers have been designing gears for hundreds of years. At that time, they did not have calculators. At that time, they did not have sophisticated computers, no MATLAB, no SolidWorks. So at that time, what they used to do is they did the hand calculations starting from the first principles and verified the results using experiments. Clearly, the hand calculations and experimental results, they do not match 100%. No experiment is complete without an error. And the reason for that is when you perform the hand calculations, the basic assumptions are the plane sections remaining plane. The calculations are in 2 dimensions, but the actual loading conditions are 3 dimensions. The plane sections do not remain plane. For an example, if you look at the gear, the first level of assumption is the cross section is uniform. That is how we derive the beam strength equation. But that is not true because gear has the curvature, so the cross section changes. So to account for these assumptions, they added these safety factors. So this y, or the Lewis form factor, you can think about is a safety factor that compensates for the assumptions in the basic hand calculations. Everyone understood this? So think about it like a factor of safety. So now how do we find out Lewis's form factor? Lewis's form factor Y, and this equation will be given to you. This is given in the textbook as well, is 0.124, 0.684 divided by number of teeth for 14.5-degree pressure angle, composite, and full involute. So what do we mean by composite? Sometimes the gears, because of the application, may not have a complete involute profile. There could be some modifications to the involute profile. There could be some shavings. There could be some additional surface treatment that would change the shape of the profile. And that gear is called as the composite gear. So next, Y is 0.154 minus 0.912 divided by T for 20 degrees full depth, and Y is equal to 0.175 minus 0.841 divided by T for 20 degrees stub. Once again, at the end of the day, Lewis form factor equation relates the strength to the load. So check this out. This is the strength or the stress. This is area. And Lewis form factor is just a number that relates the area calculations, stress multiplied by area calculation to the load on the left hand side. Everyone understood this? Now, clearly, there are a lot of assumptions in this equation. The fundamental assumption is that when we look at the beam strength equation, the loads are not moving. But that is not the case. When the two gears come in contact, what you have is the loading is not static. The loading is dynamic. So clearly, we can't use the equations for static strength when you have dynamic loading. So let me repeat this once again. So what is happening is, look at the beam equation that we derived. Here, we did not assume the load to be changing, or we did not assume the load to be moving, or we did not assume the load to be varying either in magnitude or in location. But when you are looking at the actual gear meshing, you have some dynamic effects. So we actually ignored the dynamic effects. So to account for dynamic effects, what we do is we consider something called as the velocity factor. So this equation is the basic equation, but please understand this equation is good if the loading is static. But in actual practice, the gears are not stationary. They are rotating. So what we need to do is we need to look at the dynamic effects on the gear. So for that, this equation WT is actually modified as sigma W times B multiplied by pi times M multiplied by Y. And this equation, and I will repeat this here, sigma W is equal to sigma multiplied by CV, where sigma is the strength and CV is called as the velocity factor. Velocity factor is a factor that is less than 1. So in this equation, you would use sigma W, and this sigma W is to account for dynamic effects or motion effects. Now, CV is less than 1. And I just want to give you a general idea here. So um, what I want to do at this point is look at page 1039, and that will give you the different values of CV. So for an example, if the gear is ordinary cut, what do we mean by ordinary cut? Ordinary cut means the gear that is cut with the regular cutter, not the precision cutter. So if you have not seen uh, how the gears are cut, just go to YouTube and see the gear cutting machine. So basically you have a tool, and basically you have the blank, and the tool rotates and gradually it cuts the gear. So depending upon how accurate the tool is, depending upon how precise the tolerances are on the tool, there are different types of gears, and that's why there are different grades of gear, and that's why it's the same module, same PCD gear would cost differently for different applications. So CV is equal to 3 divided by 3 plus V, where V is the centerline velocity, which is less than equal to 12.5 meters per second. So what do I mean by this centerline velocity? Centerline velocity is, think about this gear pair, the velocity at the center, which is VP, is the centerline velocity. The equation for the centerline velocity is pi times diameter of the gear dg ng divided by 60 is equal to pi times dp, which is the diameter of the pinion, speed of the pinion divided by 60. So p is the velocity of point P that is on the line of center. This is P is the point of contact. Vp is the velocity of point P. Whether you consider that on the gear or whether you consider that on the pinion, that velocity is going to remain the same. Now, so whenever you start with the gear design, first and foremost, we have to find out what is the type of gear we are going to use. Then what is the material of the gear that we are going to use? Then what is the velocity at the interface? What is the VP? Then we have to find out the value of CV, and then we have to proceed further. And just like any other design process, this is like back and forth. You have to go back and forth to sort of iterate and finally come up with the appropriate design that is safe and meets all the requirements. Now, at this point, I just want to kind of refer you to this table. This table is 28.4. So please look at table 28.4. This table 28.4 that gives you allowable values, static stress values. Now, if you look at the allowable static stress values, can you see that it gives you for cast iron, medium grade, highest grade, untreated, all that type of stuff. So can you see that these are the allowable static stress values? Everyone understood this? However, there is one important equation that is not very clear. Please look at the note at the bottom. The allowable static stress for steel gears is approximately 1/3 of the ultimate tensile strength. Are you with me so far? Can you, so basically, I will write this note again. Sigma O for steel is equal to sigma ultimate divided by 3. Do you agree with me? Or sigma U divided by 3? Now, why do I emphasize on this? Look at this table, which is a 28.4. This 28.4 table, if you skim through it, it just talks about forged carbon steel, alloy carbon steel. It does not give you lot of gradation of steels. Do you agree with me? On the other hand, if you go back to table 28.3, it gives you properties of carbon steel for 0.3% carbon, 0.4% carbon, carbon chromium steel, carbon manganese steel, and all the gradations of steel. Do you have the textbook? This is okay. So, but please refer to this. So, which means if they specify that the gear needs to be used, gear material has to be 0.4% carbon, what would you do? You would go to 0.4% carbon, minimum tensile strength, which is 580, and divide that by 3 and use that as sigma O. Everyone understood this? So I'm gonna write this down because this is very important. So question: design gear, because these are the practical questions that you will come across when you go to industry. So design a gear with 0.55% carbon, harden and temper, harden and temper. So what would you do? Step number 1, go to table 28.3, locate 0.55% carbon, harden and temper, and you see that its value is 700 Newton per millimeter square. From here, you would find out sigma O as 700 divided by 3 Newton per millimeter square. And from there, you would find sigma W is equal to CV multiplied by sigma O. And this CV depends upon the pitch line velocity. Are you with me so far? Okay. And don't worry about it. I'm going to work out a few problems from scratch. At that time, this process of going back and forth would be clear. But let me just give you the process, what's going on, and then later we are going to look at the variations. So velocity factors for different types of gears, CV is equal to 4.5 divided by 4.5 plus V for carefully cut gears. then CV is equal to, I will just write one more, 0.75 divided by 1 plus V plus 0.25 for non-metallic gears. And there are different equations for precision cut gear. There are different equations for accurately cut gears depending upon the pitch line velocity. And these values of CV, they are given on page 1039. So these equations come from page 1039. Are you with me so far? I don't think I asked you any composite gears, because when you design a composite gear, uh, the considerations are a little bit different. Because I tell you, if you design a steel gear, uh, because of the conducting property of the gear, you can easily take care of the heat dissipation. But when you design, okay, so let me take a step back. When I say a composite gear, that means the gear that could be made of composite material, which means that is non-metallic, like plastic, nylon, some type of exotic gear. Sometimes there could be a composite profile gear, which means you have an involute profile that is somehow modified, and that they call it as composite profile. So I haven't given you any homework on, so to speak, non-metallic gears. I have not given you any homework on composite gears. We are just following complete involute or involute, the stub gears, so a standard gear profile. So again, that's metal, right? So pardon me. Oh, okay, yeah. So okay, okay. So for that material, you can find out. I didn't understand the question. So for that material, you will follow the exact same process, but you will get the properties. And I do not think for that material the properties are given in the textbook. But if you were to just look at the material database, that those gears properties will be available to you. The procedure is exactly the same. Okay, I didn't understand. You're referring to the homework. Oh yeah, that is where, right. That is where you will use a CV for non-metallic gears for that material. Or if you have a plastic or a nylon, then you will use CV for non-metallic gears. Okay. All right. Now, what I want to tell you is, as we talked about, the gear loading is not a static loading. So gear loading is a dynamic loading. Now, when we are trying to design the gear, what is the process? What is the process in designing the gear? So what we do is, we actually go with the first level of approximation. We use the beam strength equation. Remember the beam strength equation, WT is equal to sigma W multiplied by B multiplied by pi times M multiplied by Y. This is a very simple equation for beam strength equation. This equation becomes simpler because the value of B, okay, I think I need to go back and write this. So B value here is usually 10 to 12 times module. So the face width of the gear is proportional to module. So what that means is that entire equation will be in terms of module. Everyone understood this? We know the value of WT. we can find out the value of CV, we can find out the value of sigma W, all that stuff. So at the end, I'm gonna get value of module. Once module is found out, for practical purposes, my gear is designed. Everyone understood this? But I do not know if that gear is strong enough, if that gear can withstand the dynamic loading, or whether or that gear will sustain the continuous contact. So I need to check gear for the dynamic load, and I need to check the gear for the wear load. So right now, based on the beam strength, we have a gear, but we do not know if that gear is good enough for the loading or for the wear. So these are the next steps. So what we want to do is we want to find out the dynamic load on the gear, which is called as the dynamic tooth load. So WD is equal to determination. And I will, in the next class, I will give you a step-by-step recipe for gear design. So right now, I just want to talk about the important concepts in gear design. But in next class, I will give you a step-by-step recipe, and we'll follow the step-by-step recipe and work out the problems. So determination of dynamic load. So dynamic load is the tangential load plus intermittent load Wi. Tangential load, we already know. Tangential load is a design parameter. So for an example, how would you find out the tangential load? Tangential load, if you think about it, is nothing but Wt multiplied by the radius r. Wt multiplied by the radius r gives you torque. So torque is equal to Wt multiplied by r. So that gives you the tangential load. Now, what about intermittent load? For intermittent load, there is this long equation, and I'll talk about how this equation came into existence. So this is B times C plus Wt divided by 21V plus square root of Bc plus Wt. Now this complex looking equation comes from something called as Buckingham pi theory. Pi equation. What is this Buckingham pi equation? So please try to understand, there is an entire branch of engineering that deals with something called as the dimensional analysis. And the dimensional analysis means that how do you perform experimentation on small proportional objects and still conclude about the real life big objects. So for that, what you need to do is you have to maintain the kinematic similarity, geometric similarity, dynamic similarity, and find out the kinematic proportional constants, dynamic proportion constants, and geometric proportion constants. So based on that analysis, this equation is derived. And you can look it up. There is an entire branch which talks about the dimensional analysis. But what this equation is about, what are the key parameters here? Everyone agrees that the magnitude of the intermittent load will be proportional to velocity. If the velocity is high, then continuously the load will impinge, and then the intermittent load is going to be high. So this equation has V parameter. That V is nothing but the pitch line velocity. So this is the pitch line velocity. B is the face width. And C is this constant. And please try to understand, when you do the dimensional analysis, you can add dollars to pesos. Okay, that is the how it works, because the constant of proportionality takes care of it. So uh, typically we can't add dollars to pesos, but in the dimensionality analysis, you will see the terms. One term would be expressed in meters, other term would be expressed in millimeters, but at the end, the constants are adjusted in such a way that those variations are compensated. So there is somewhere 1,000 floating around that actually compensates for conversion. So please understand, C is called as the deformation factor. And there is a lot of discussion on deformation factor. So what is this deformation factor? Now, deformation factor C depends upon the error. So then the class of the gear, then form of the tooth, and the material of the gear. And there are different ways of finding the value of C. So now it is super important at this point that I want you to refer to table 28.5. On table 28.5, what you have is, you have the material. And this material, you have pinion material, you have the gear material, you have the tooth profile, and then what you have is, you have the values of the deformation factor for different values of error. Now, this error is called as the tooth error in action. Now, what do I mean by the tooth error in action? So when you are trying to cut the gears, depending upon your requirement, you use different type of cutter. And based on the grade and the quality of the cutter, the error changes. So if you were to look at the total tooth error in action, that goes from 0.01 millimeter, 0.02 millimeter, 0.04 millimeter, 0.06 millimeter, and 0.08 millimeter. Now, what that means is, if you use a cutter with minimal error, then your deformation factor is going to be low. If you use a cutter that is worn out, or that has the more error, then your deformation factor is going to be large. If your deformation factor is large, that means your dynamic load is going to be large. And what it means, if think about it, like if your gears are not precisely cut, they are going to run noisy. What that means? That means the intermittent load is significantly higher if the gears were to cut by a precision high accurate cutter. So this value of C you can pick up from the table, or if you like, this value of C can also be found out from this equation, K times E divided by 1 divided by Young's modulus of pinion plus 1 plus Young's modulus of gear. So WD is nothing but the dynamic uh, load, and dynamic load is at a summation of uh, tangential load WT plus intermittent load. And intermittent load is computed with this equation. But I just want to tell you one important part in this big equation. This B is the face width that is given in millimeters. This value of C is given in Newton per millimeters. So at the end of the day, what you have is, you have the product of B times C that is going to give you in newtons. Everyone understood this? You are adding WT. So to add WT, you need to convert WT into newtons, and V, which is the pitch line velocity, has to be in meters per second. So this velocity, pitch line velocity, has to be in meters per second. So these are some important steps. I'm going to stop here. We haven't finished the important concepts. After the dynamic load, we have to talk about the wear load. Then we have to talk about the endurance strength of the gear. And finally, that will make the gear design process complete. Then what we would do is, I would give you the recipe, and then we will work out 1 or 2 problems. With that, I'm going to stop here, and we will continue the discussion in next class.